Welcome back, guys. In this video we are looking at more volume problems. We're finding volumes of solids of revolution. In this video we're going to see some washer examples, and we're going to look at axes on all sides of our region. If I've got two regions here, here's region 1. It's that black region, and that region 1 is bounded above by y equals the cube root of x, and it's bounded below by by x equals 4y. Region 2 is bounded by the y-axis. It looks like the horizontal line, y equals 2, and it's also bounded by the cube root of x, that graph. We're going to take these and we're going to revolve them around axes. Now, a couple of things you should know with all of the problems involving solids of revolution in this section. You're either going to have disks or washers. So you're going to have to decide whether after you rotate or revolve a region around a line, the resulting cross sections are disks or washers. That's just like a disk with a hole in it. You're also going to have to decide whether you integrate with respect to x or with respect to y, and that's going to depend entirely on which way you're slicing. And your axes can vary. It could be the y-axis or the x-axis, but it could also be a line on any side of that region. So you might have axes to the left of the region, or to the right of the region, or below the region, or above the region. Those are all the possibilities. But in every case, if we're looking at vertical distances, you're going to find the top y value and subtract the bottom y value. And if you're looking at horizontal distances, you want the larger x value minus the smaller x value, and the larger x values are farther to the right. See, x equals 8 is over here, x equals 4 is here, x equals 0 is here, x equals -2 is over here. So larger x's are to the right, so we're going to have x on the right, that's my larger x value, minus my smaller x value, which is x on the left. So we're going to keep coming back to this over and over again. And we're going to look at when we have disks versus when we have washers, whether we're integrating with respect to x or y, and what happens when the axis is to the left, the right, above, or below. But if you keep this in mind, I think it's going to be enough to figure, well, this plus all of this is going to be enough to figure all of this out. So let's take region 1, let's say, and revolve it around x equals 8. As our first example. Now the first thing I always do whenever I'm doing any of these problems is I sketch my region. This is not to scale. Here's x equals 8, here's y equals 2. It looks roughly like that. It's a line, and that's supposed to be the part of the cube root graph. We're taking that and we're revolving it about this line, x equals 8. X equals a constant, that's a vertical line. So first things first, sketch the region. And then to help us visualize, I want to sketch the reflection of that region across the axis. So I'm imagining taking this and then reflecting it over here. So it's almost as if I took my piece of paper, I folded it in half, and then I traced it over on this side. Now my sketches are never perfect, and I don't expect your sketches to be perfect either, but we're just trying to get a rough idea of what's going on here. So we're going to sketch the region and sketch the reflection about the axis. And the axis of revolution this time was x equals 8. So if this distance is 8, I'm going to go out to 16, obviously not to scale. And if this line goes up like that, the reflection is going to go down like this. This goes down like that, I imagine it's going to kind of go down like that. It's not perfect, but close enough, right? Good enough for us. And now, once we've done that, we have to imagine whenever I'm doing a solid of revolution and I'm using the disc or washer method, I always have to slice perpendicular to the axis, because when I slice perpendicular to this axis, the resulting solids are discs or washers. So we're going to slice either the region or our imagined solid perpendicular to x equals 8. So if I slice, well, let's think about what this looks like. If I took this and I rotated it all the way around, what would we see? Well, I think we would just see like a bowl. Wouldn't we see sort of a weird bowl shape? Wouldn't it look kind of like this? But then if we look inside the bowl, I think we're going to see a cone cut out, a cone that's cut out from this piece. There's like a missing cone inside. So it's kind of a strange bowl. You flip it over and you look inside and there's like a cone missing. And very straight edges. Say, okay, well that's kind of what we're trying to find the volume of. Okay, so now I'm slicing perpendicular to this axis. When I do, I get something that looks like this. This is hard to do. See, that's what my disc would look like, but there's a gap here in the middle. So these aren't discs, these are washers. Looks like Salvador Dali made it or something. Alternatively, say, Miss Townsend, I'm not an artist. It's okay, me either, right? You're going to slice the region perpendicular to the axis into rectangles. And imagine taking that rectangle and going all the way over here. You're rotating that rectangle around. Now, if you looked at it with some dimensions, it's going to look like a washer because of that big gap. So you have to decide, after you've sliced your region perpendicular to the axis, you have to decide whether you have discs or washers. So that's our next step. Decide or choose. Do you have a disc or a washer? And the way you can choose is to look at the relationship between your original region and that axis. If there is a gap between your region and the axis, the resulting solid is going to be a washer, or that slice will be. The resulting slice is a washer. No gap. So that means my region goes all the way up to this. Well, then there's not going to be that missing piece in the middle. So we'll have a disc. Okay, so we've got a gap. If I take that little piece and I rotate it around, I'm going to see something that looks like this. Or I'll try to draw it out here. It looks like this. Looks a little better out here, doesn't it? Okay, so that's my washer. Now, the width of my washer, or the thickness of my washer, is the width of that representative rectangle. We've sliced perpendicular to x equals 8, which also happens to be perpendicular to the y-axis. That's a little tiny vertical distance. So the width or thickness of my washer is delta y. Now, if I take this and I set it up on its face, those aren't ovals, those are true circles, even though it might not look like it. That's what my washer looks like. So if I want the volume of this, I've got to find the area times the thickness. Okay, oh wait, I'm so sorry, I'm getting ahead of myself. So we had to choose between discs or washers. There was a gap, so we chose washer. Now after you've chosen between discs or washers, you have to decide if you're integrating with respect to x or with respect to y. And we just did that too, but I want to put that on your list of things to do. when you're choosing between delta x and delta y, you want to look at the width of that representative rectangle, or alternatively the width of your disc or washer. If your width is a tiny vertical distance, I shouldn't say equals tiny. Width is then we choose dy or delta y. If it's a horizontal distance, so if my rectangles are like vertical, so if it's tiny horizontal distance, I've got delta y. If my rectangles are vertical like this, the width is delta x. I've got a tiny horizontal distance. So you have to choose. Disc or washer, we chose. There was a gap, so we've got a washer, and then we choose between delta x and delta y. We look at the picture, we see delta y. Okay, now after we've made those choices, we look at the geometry of this one shape, this one slice. If I can find the volume of the slice, I can find the volume of the whole thing. Volume is still just area times delta y or x, whichever is appropriate. In this case, the thickness of our slice is delta y. How do you find the area of a washer? It's actually pretty simple. You need to find the area of the larger circle, which is pi r squared, and then you have to subtract the area of the smaller circle. I'm going to use little r or lowercase r for the radius of the smaller circle. The area of the smaller circle is also pi r squared. You just use the other r. So you've got this area minus this area is the area of that face, and then you're multiplying by delta y. Now, on your test over this material, I'm not going to give you these formulas. And I know a lot of students are saying, oh, memorization, I don't want to have to memorize anything. And I agree, I don't want you to have to memorize anything. I want you to know where everything comes from. The way you memorize this, the way you learn this, is to look at that picture and say, what's the area of this? And it's just going to be the area of the big circle minus the area of the little circle. I take this whole area and I take that piece out. That's all. And so I get this formula. So if you really understand the geometry of this, it's not memorization. It's just looking at the picture and saying big area minus little area times delta y. And if I take an area and I multiply it by delta y, that's giving me a volume. So no memorization. It's just understanding. Understanding this. If you understand this, then you know what the formula is, because you know where it comes from. Okay, so let's factor out the pi. So I've got large radius squared minus small radius squared times delta y. All right, so now I just need to find the larger radius and the smaller radius in terms of y. Now this is a little bit hard on my picture because of the way I've drawn my picture. It's so thin. It's very, very small. I'm going to draw it a little bigger so it's a little bit easier to see. So this is really not to scale. I'm so sorry. It's like not a good picture on the other side. That's all right. See my pictures? No, your pictures probably look much better than mine. See, I was gonna say my pictures look like yours, but no, you guys are probably better artists than I am. Okay. So we've taken this and we've sliced perpendicular to this axis, like this, bam. And that's giving us a washer. Oh, that's much better this time. Now, we also said, same thing, I'm going to take this representative rectangle here and I'm going to rotate it around, and when I rotate it, it's going to appear over here. So it's going to be like on this side it's that, and then on this side it's that, and it gets rotated around, and so we get this whole washer, that washer piece. Now the inner radius and the outer radius can be found by looking at the distance from our axis to that rectangle, or the axis to that inner point, that's our inner radius, and then the axis all the way to the outer point of the washer, that's our outer radius. Same thing if we use the rectangle. I'm going to use the rectangle because I think it's a little easier to see than trying to draw like lots of little arrows in there. So the inner radius goes from the axis to the representative rectangle. That's the radius of the gap. It's that radius right there. And the outer radius goes all the way out to the outer edge of that rectangle. The outer radius in this picture, I'm going to use the blue, it goes from the axis all the way out to there. And then we want both of these, because our representative rectangle looks like this, we want both of those radii in terms of y, because that width is delta y. Alright, let's mark up this picture. This top curve was supposed to be y equals the cube root of x. I know it's not to scale, but it's made it easier for us to see. And then this line is, x equals 4y. Alright, so volume of one of these guys is area times delta y. Area is the area of the large circle minus the area of the small circle. And we can factor out the pi's, leaving space for the larger radius and the smaller radius and delta y. Okay. Now I just need the inner radius in terms of y and the outer radius in terms of y. Well, outer or inner radius, notice that it's a horizontal distance. Whenever you have a horizontal distance, you're going to do x on the right minus x on the left. That is not going to change. It's always this x value minus this x value. Now, because we're integrating with respect to y, I need this x value in terms of y and this x value in terms of y. But it's still this x value minus this x value, okay? Okay, so x on the right. Well, x on the right, what's given by the x value on that line? Well, x equals 8 on that line, so it's just 8. And x on the left is the x value on this line as a function of y. And fortunately, they already gave us x as a function of y. They told us that x was 4y, so I don't even have to rearrange anything. So this is x equals 4y, but I'm talking about the ith washer, so I'm going to put a little y sub I because I'm picking a particular y value on that subinterval. Okay, so this is little r. That's the inner radius. I'm going to sub that in right there. The outer radius is very similar. It's horizontal. It's x on the right minus x on the left. That has not changed. And x on the right for the outer radius is still 8. Now x on the left is the x value on this curve. So I need x as a function of y on this curve, this pink curve. Well, it's not too bad. The equation of that pink curve is y equals the cube root of x. So let's solve for x by cubing both sides. We get x equals y cubed. So there's my x as a function of y. And I'm going to sub that in. X on the left as a function of y is y cubed. I'm going to use y sub I cubed because we're picking a y value on that ith subinterval. Okay, so that's my radius, my large radius. And that's the volume of one slice, which means the total volume is the sum as I goes from 1 to n of those slices, and then we take the limit as the number of slices goes to infinity. Or as the width of that slice, delta y, becomes infinitely small, so small that we call it dy. Now you don't have to do the Riemann sum every time, but on your test over this material, I will have you do the Riemann sum a couple of times just to demonstrate that you understand how this works. The Riemann sum is the basis of the entire chapter, and I really want to make sure you understand not just how to set up the integrals, but the concept. So the limit of this is an integral. I'm going to factor out my pi. In the limit, we don't just have some y's. We don't have just y sub I on the ith subinterval. We get all the y's. So we don't need that I anymore. All of that is multiplied by this delta y, but it's become infinitely small, so small it's an infinitesimal. We call it dy. Now, the bounds here are the bounds for y in the original region. So the original region is this region bounded by the pink curve and the orange curve. I'm not worried about the reflection over here. That's just something I drew to visualize what's going on. And we're integrating from taking this rectangle, this piece, and then rotating it around and around for every single rectangle for infinitely many rectangles. So this region is telling us what happens over here. When I rotate it, it appears over here. So I don't need to worry about bounds for that guy. But we're looking for bounds for y, so y starts here at the bottom, so y equals 0, and then it goes all the way up to the top. And this was x equals 8. If I substitute x equals 8 into the cube root function, the cube root of 8 is 2. So obviously not to scale, but y starts at 0 and goes to 2. So go from the bottom to the top, 0 to 2. And that's the volume. Now I'm not going to spend time, I'm not going to spend time evaluating this, but I do want to show you how we would evaluate it. If I wanted to evaluate this, I could do u sub for this one, but I can't do u sub for this one. The derivative of this is just a -4. So we could do u sub here, but here we'd have to write it twice in FOIL. So I'd write that twice. And you could write this one twice in FOIL too if you want to, so you can avoid the u sub if you prefer to. Then first times first is 64. Outer times outer is -8y cubed. Inner times inner is the same, so I've got -16 of those. And last times last is y cubed times y cubed. Add the exponents, that's y to the 6th. And you've got a rule for that, and a rule for that, and a rule for that. And this one you can do as a u sub, or you can write it twice in FOIL, distribute the negative, and use the power rule. And I think you know how to do that. My concern here with this video is to make sure that you can get here. So look what we did. We were revolving it around a horizontal line. So we sliced perpendicular to, or excuse me, I said horizontal, vertical line, excuse me. We were rotating around a vertical line. So when we slice perpendicular to a vertical line, we get slices like this. So that means we're integrating with respect to y. And that means when we're using the disc or washer method, the radii look like this. I look at my picture tells me, hey, that's horizontal. I've got to do x on the right minus x on the left, x on the right minus x on the left. Now, whether it's right or left, it's going to change from problem to problem, but one of those is going to be the axis. If our region is over here and the axis is to the right, x on the right is the equation of the axis, x on the left is given by one of these bounding functions. But I could have just as easily taken this region and rotated it around x equals -1. And then x on the right would be the function, x on the left would be the axis. So there's not a hard and fast rule for whether the axis should go first or last, but you always do larger one minus smaller one so that the radius is truly a positive value, because radius is going to be positive, right? Except for when it's 0. Then it's not much of a radius, but still, we're never going to get a negative radius. That doesn't make any sense. So you're going to do the one on the right minus the one on the left, and one of those will be the equation of the axis, and the other one will be a function. Now careful here, we need x on the left as a function of y. Sometimes that requires solving for x. Sometimes x is already given to us as a function of y, and there's less work to do. But that's how we got our radii, and it's just area of the big circle minus area of the little circle times the thickness. And then if you factor out the pi, you get that. All right, so that was our first example. We took R1 and we revolved it around x equals 8, and we got this. We got this sort of bowl shape, and if we looked inside the bowl, there's like this cone cut out of it. The volume of that bowl is equal to whatever that is if we were to work it out. If you get a negative volume, you know you made a mistake somewhere. Volume should always be positive. Okay, so we're going to find the volume of that bowl by evaluating that integral. So we took that region and we revolved it around a line to the right of the region. We could also revolve it around a line to the left. And we could also revolve it around a line that's below the region or above the region. How about, let's revolve it about a line to the left. It's actually going to be very similar to what we just did. So let's take region 1, and instead of rotating it about x equals 8, let's rotate it about x equals -1 instead. Always start by sketching. Here's my not to scale picture. And I'm rotating it around, oops, x equals -1, which because of this scale that I've used, x equals -1 is right here. And when I rotate around x equals -1, this is 8 units long. We've got a little gap here of 1 unit, so we're going to have a little gap here, and we're going to draw something that's 8 units long. So I think it's going to go all the way out to -10, -2, -4, -6, -8, -10. It's going to look like that. It's going to meet right here. It's kind of a straight line from there to there. Oh, this is such a bad picture. I'm so sorry. It does not look good at all. There, maybe. It's a little better. That's bad. That's okay. That's all right. We get the idea. So we're taking this guy and we're rotating it around here, and it's going to look something like that. Now we're going to slice perpendicular to the axis again. So we get discs or washers. Okay. Before we go on, let's write down the problem. We're rotating or revolving. I keep saying rotate, but I really mean revolve. We're going to revolve R1 about x equals -1 this time. And then we slice perpendicular to this axis, and since it's vertical, we get another delta y integral. If I slice my original region with a rectangle that's perpendicular to this axis, that width is delta y. And what I get here in my slice is I see something like that. It's a washer again. So what did we do? Sketch the region. And of course, you want to also sketch the axis. And then sketch a reflection. about that line. Okay, you do the best you can. It doesn't have to be perfect, but just try to get the right idea. And then you want to slice perpendicular to the axis. Always perpendicular, because when we do, we're going to get discs or washers. Now, when I slice perpendicular to this axis, I see this. Any idea what the shape is going to be? Well, I think from our perspective, it's going to look like this. But if you look inside, it's like a bowl, but it doesn't. You're going to be able to see right through it. There's going to be a big hole in the bottom. It's not a very good bowl. But if you were to look at it from the top, it's going to have like a piece missing in the middle. Do you see like that missing piece? So we're just going to have these like little shapes on either side. But yeah, from the side, from the outside, it's going to look like it's one solid piece, and then you're going to look inside and be like, hey, there's a hole in that thing. So that's the volume, or that's the solid that we're trying to find the volume of. We slice perpendicular to the axis, and you can do the representative rectangle thing, like I did here. You can also do the representative disc or washer. And now you have to make some decisions. You're going to decide, is it disc or washer? So gap or no gap? If there's a gap, it's a washer. No gap, and remember that's a gap between the region that you started with and the axis. It's a disc if there's no gap. Here's my region, and there's definitely a gap between that region and x equals -1. So I know I'm dealing with a washer. You've also got to decide, is this a delta x or a delta y? Is it going to be an integral in terms of x or y? And the way you can do that is to look at the width of the representative rectangle, or alternatively, look at the width of your little washer. Little distance up and down, so that's delta y. And then once you've got whether it's a washer, whether it's a disc or a washer, whether you're integrating with respect to x or y, then you can write down the formula for that, and then just find the inner and outer radii, because it's a washer. Okay. Keep this picture up here. So we know V sub I, that's the volume of a washer. The thickness of the washer is delta y. So we're taking area and multiplying by delta y. Area of a washer is area of the large circle minus area of the small circle. You can factor out the pi. Now you just have to find the outer and inner radii in terms of y, in terms of that variable there. Now remember how we do this. The inner radius starts at the axis and goes out to that point. Or alternatively, it's a little easier to see out here. It starts at the axis, and it basically fills the gap. Like, it's the radius of that gap, that piece that we're taking out. So it goes from the axis out to the inner edge of your representative rectangle. That's horizontal, so we're still doing x right minus x left. X on the right is given by the x value on that curve. And that curve was given by the equation y equals the cube root of x. If I want to get x by itself, I just cube both sides, so I've got x equals y cubed. Same thing. So I need x as a function of y, that's y cubed. And we kind of knew that already because we used the same region for the other problem. The x on the left is -1. So you're subtracting -1. That means you're adding 1. Actually, I think that makes sense geometrically, doesn't it? If x on the right is this value, which in terms of y is y cubed, aren't I just taking that and adding that little distance of 1? I hope you see that that's just a 1, and then we're adding that x. It's this x plus the 1, or this x minus a -1. Same thing, gives us the x plus 1. So the inner radius is y sub I cubed plus 1. Outer radius, similar. You always start at the axis, and you go out, not to this part of the representative rectangle, but the outermost edge of the representative rectangle. Because that outermost edge, that corresponds to the outermost edge of that washer. So I need x as a function of y on this curve. And we know from earlier, or if we don't remember, we can look it up, that x is equal to 4y on that curve. So we don't have to solve for x as a function of y this time. Oops, didn't write it down yet. I need x on the right minus x on the left. X on the right is given by 4y. X on the left is still -1. So I've got 4y sub I plus 1. I'm filling that in. Okay, that's the volume of one washer. I want the volume of the whole thing. Now I'm not really computing, I'm just setting this up. I'm going to say, find the exact volume. And the exact volume is the limit as the number of slices goes to infinity, or alternatively, as that delta y goes to 0. And we're summing these as I goes from 1 to n, because there were n slices. It's the volume of the first plus the volume of the second plus the volume of the third, all the way up to the volume of the nth. And that is the definition of an integral. I'm going to bring my pi out front. That's going to be a 4y plus 1 squared. That is a y cubed plus 1 quantity squared. Delta y becomes dy in the limit. You don't need the i's. And we are going to integrate from one y value to another. For this picture, y starts at 0 and ends at 2 for the original region. So that's that. Okay, both of those were integrals in terms of y. Let's look at what they had in common. Why did we integrate with respect to y on this one? And then also on this one? I hope you see that we integrated with respect to y because our axis was vertical. If I have x equals 8 and I slice perpendicular to this axis, all those rectangles are going to be horizontal, and all of them are going to have a width of delta y. Or alternatively, you can look at your washers or your discs and you see they have a width of delta y. Same thing is true down here. I've got a vertical axis. The representative rectangle, when I slice perpendicular to that axis, it's horizontal and it has a little height of delta y. And that height of your washer or disc is also delta y. Okay. So that's that. Now let's take the same region. Instead of rotating around a vertical axis, let's rotate around a horizontal axis. So let's rotate R1 about y equals 2. And this actually was y equals 2. This is the point y equals 2, x equals 8, remember. Okay. first thing I do, sketch my region and the axis. Then we want to sketch the reflection of that region about the axis. So basically I want to take this and I want to flip it up here. So I'm going to see the same image but just flipped in a reflection. So this is y equals 2, so I guess y equals 4 is where we're going to see it. This is going to become that line. This is going to become something that looks like that. It's not very good, but you get the idea. If you look at this, when you look at the solid, it's going to look like this from the side. It's going to look like a cone. But if you look inside the cone, it's going to have like this piece taken out. It's sort of weird, like bugle shape. You ever do that Gabriel's horn problem? Oh, not yet. Not in calc. We'll probably do that later this semester. But it's got this sort of bugle shape that's cut out of the middle of that cone. On the outside it looks like a cone, but inside it looks like this piece has been chopped out of it. Okay, so that's what the volume that we're trying to find. The volume of something that looks like this with this other piece, this sort of weird. Also, it's two-dimensional. Not doing a very good job drawing that. Cut out of it. Okay, so this is our region. And we revolved it around this axis. And now we want to slice perpendicular to the axis. This time when we slice, we're slicing it like this, perpendicular to y equals 2. I've got washers again. Notice this time my washer has a width or a thickness of delta x because we sliced perpendicular to the x-axis because y equals 2 is horizontal to is horizontal and the x-axis is horizontal. The y equals 2 and the x-axis are parallel to each other. So once you've sliced perpendicular to the axis, you might also slice using a representative rectangle. I'm going to use this representative rectangle. Actually, this was my region. So here's my representative rectangle. When I reflect it, it ends up there. Okay. And I've got either representative rectangles or washers or both. Now I need to decide, is it disk or washer? Is it delta x or delta y? And is it delta x or delta y? Is my integral in terms of x or y? Or am I dealing with disks or washers? Well, notice here's my region and there's a gap between that axis and the region. So I'm going to say gap implies I've got a washer. Okay. And the width of this disk is delta x. So you can do that, or I said disk. The gap of the wash, or the width of the washer or thickness of the washer is delta x. Or alternatively, the width of the little rectangle, the representative rectangle, is delta x. Okay, so we got washers, we got delta x. Now we want to state the volume of one piece, one slice. The volume of the ith washer. Well, we know how washers work. Washers look like this. This time, the width is delta x. And we still have area times the width or the thickness, delta x. Area of a washer is just area of the big circle minus the area of the circle we cut out. So it's that area minus that area, where big R and little r are the radii of those two circles. And we can factor out the pi if we choose. So I just need to find the large radius and the small radius. I need big R and little r, or if you prefer, outer radius and inner radius, large radius and small radius. Okay. So I'm going to draw them on my picture. Now, when you're finding the radii, do not calculate your radius by going to that reflected region. You want to go from your axis to the original region, the one that you had before you started reflecting anything. So this was my original region, this region down here, below y equals 2. So my radii are calculated using this region, not that reflected piece. The inner radius starts at the axis and goes here, or alternatively, using representative rectangles, it starts at the axis and goes to that innermost edge of that representative rectangle. That's little r. And capital R, the outer radius, goes to the outermost edge of that representative rectangle. So notice, oh, hello, it's zooming very quickly. Notice that this little radius starts at the axis and goes to here. The outer radius starts at the axis and goes out to here. So we're putting those two pieces together. It's the same as what we would see if we actually did it right on our washer. It's a little bit difficult to see, but that's exactly what we're going for. Okay, let's zoom out a bit. All right, so I need that large radius. It's vertical, so what are we going to do? We do the top y value minus the bottom y value as functions of x. Okay, that's easy enough. The top y value is given by the equation of our axis, y equals 2. And the bottom y value for our larger radius is given by y as a function of x on this line, this pink line. Well, the equation of that line was x equals 4y, but I don't want x in terms of y this time. I want the bottom y value. I want y, but in terms of x. So I need to rearrange this, solve for y. So y is 1/4 x on that line. And we're going to use x sub I because we're talking about an x value in the ith subinterval. That's my large radius. Top y minus bottom y. Inner radius is the same. It's also vertical. You're going to do the top y value minus the bottom y value as functions of x. Top y value is 2. The bottom y value, well, it is the y value on this curved piece. So it's the bottom y value for little r. That's what we're looking for this time. And on that curve, y was equal to the cube root of x. All right, so we already know what y is in terms of x on that one, so it's just cube root of x sub I. So the inner radius is 2 minus the cube root of x sub I. We're going to square that. Do this, that's the volume of one thing, one washer. And then we can go from that all the way to the integral if you prefer, or we can continue to practice the Riemann sum. I'm just going to go straight to the exact volume. If I want the volume, I add those up as I goes from 1 to n. This is the sum of the volumes. Took the volume of every single disk for n of them, and then I added them up. So I said this is the approximate volume. And I said I don't want approximate, I want exact. So I'll take the limit as n goes to infinity. And that's equal to this. Don't need the i's anymore. Got pi times outer radius squared minus inner radius squared. If you want, you could write that as x to the 1/3. Delta x becomes dx in the limit. And we integrate from x equals something to x equals something else. Now those bounds for x come from the original region. X started at 0 and ended at 8. So that's that one. Now that was when we rotated about y equals 2. If we rotate about y equals -1, it's going to be very similar. Just instead of having the radius above us, it's going to be below. But notice in both cases, if I have the radius here or here, they're both the axis here or here. If the axis is horizontal and you slice perpendicular to the axis, you're going to get delta x integrals, delta x integrals both times. The only difference is that y top minus y bottom. If the line is above the region, the top y value is the equation of the axis, the line, that horizontal line. And the bottom one is a function of x. Now, if the line is going to be below, top minus bottom is going to be equation of a function minus the 2, or minus the equation of the line that's below us. So let's do that one, and then we'll be done. I'm not going to evaluate this, but if we did evaluate this, we'd find the volume of that thing. Last one. You guys are troopers hanging in there with this long video. All right. So we're going to rotate R1 about y equals -1 now. I'm going to try to do this quickly because you probably already know how this works. You're probably already starting to get it. So here's x equals 8, here's y equals 2. We're rotating about y equals -1. Sort of weird Pac-Man-like shape. I'm so sorry, that is horrible. Ugh. We do the best we can. Okay, so I'm taking this. What do we always do? Sketch the region and the axis. Then we sketch the reflection. About that line. And then remember what we do? We slice perpendicular to the axis. And you can slice the region itself into representative rectangles, and imagine taking that rectangle and rotating it around. So that rectangle up there ends up down here. Or you can say, I'm slicing the whole solid. This is a solid, it has a big hole in it at the bottom, has a big hole in it at the top. But you're going to see when you look at it, oops, it's actually going to be much smaller over there. It's going to be something that looks like this. But if you look inside, you're going to see it has a big hole at the bottom. And it's got these weird straight edges inside. But yeah, we're taking this region and we're rotating it around. And then on the outside, it's going to look sort of like this. Anyway, that's the idea of it. So I'm going to slice my solid perpendicular to that axis. Notice I have washers, because this was my region, right? And I took it and I rotated it around. There is a gap between that region and this line y equals -1. Okay, so we slice perpendicular to the axis. Now we decide between disk or washer and delta x or delta y. I see a gap. So that means we've got a washer. A gap between this region and that line. Look at that. There's a huge gap between that region and the line. That region doesn't even touch the line that we're revolving around. So we've got a washer, and then we look at the width of that washer. I see delta x, or the width of that representative rectangle. It's delta x. Okay, so now we're going to state the formula for V sub I. So V sub I is area times the thickness, which is delta x this time. area of a washer, this space, it's area of the large circle minus area of the small circle. Factor out the pi. Okay. Outer and inner radii, from starting at the axis and going to the innermost edge of that washer, or alternatively starting at the axis and going to the innermost edge of that representative rectangle. That's little r. And big R goes from the axis out to the outermost edge, or from the axis out to the outermost edge of the washer. So that's what we're looking at, from here to here or here to here. Notice their vertical distances. So r sub I is the top y value minus the bottom y value. And the top y value is given by y as a function of x on that curve, that line. And they told us earlier that x was equal to 4y on that line. Whoops. If x is equal to 4y, that means y is equal to 1/4 x. So I need y as a function of x on that line. And the bottom y value is just y equals -1. So my inner radius is 1/4 x sub I plus 1, which makes sense. It's this y value, and then I'm adding that 1 unit to it, that distance between the x-axis and y equals -1. That's 1. And then I'm adding that to that y, and that y value is given by 1/4 of x. So that's our outer radius, or excuse me, our inner radius. And the outer radius goes from this curve, that's our top y value, to this one, that's the bottom y value. And I know I'm doing top minus bottom because it's vertical. Large y minus small y. Y as a function of x on this curve was given to us earlier. That was x sub cube root of x sub I, if we're talking about an x value on the ith subinterval. And we're subtracting the bottom y value, which is -1. So we've got the cube root of x sub I plus 1 as our outer radius. Let's zoom out a little bit. Let's put all our pieces together. The outer radius, the large radius, is this. The inner radius is this. And that's the volume of one piece. Then you want to find the volume of the whole thing. So the exact volume is the limit as the number of slices goes to infinity of the sum as I goes from 1 to n of the v sub I, which is all of this, which is defined to be this integral. You don't need the i's anymore. We get all the x values in the integral because all of those washers are infinitely thin. So thin we call them dx in thin, or in thickness. And we integrate from one x value to another. We look at our region. X goes from 0 to 8. Now this is not the volume, but it's a formula that represents the volume. If I want the volume, I've got to write this twice in FOIL. We could do a u sub here, or you could write this one twice in FOIL, distribute, anti-differentiate using power rules, and then plug in 8 and 0 and subtract using the fundamental theorem of calculus. So, whether that line is below your region or above your region, you're going to do top minus bottom if those radii are vertical. Top minus bottom, or top minus bottom. The top one might be a function and the bottom one might be the equation of the axis. Or it could go the other way. The top one might be the equation of the axis and the bottom might be the equation of some function. But either way, you're doing